Multi-class classification is a machine learning problem where the goal is to classify inputs into more than two categories. Of course, dear friends, in binary classification, we mainly used on sigmoid function, where in multi-class classification, we use softmax function. Happy morning, dear friends. Here's yours, Dr. Rajanta. Welcome to Demystify with Ajay. Dear friends, today we are going to discuss multi-class classification with logistic regression. Before that, let me just have a recap on mathematical intuition behind logistic regression. Dear friends, logistic regression is one of the simplest and most widely used algorithm for classification task, particularly binary classification. While it shares some foundational similarities with linear regression, it modifies the approach to ensure that the output represents probability rather than continuous values. Let's break down the mathematical intuition behind logistic regression. The step one, yes, it's just starting with a linear model. Dear friends, in linear regression, we model the relationship between the input future x and the target y using the linear equation y equals w transpose x plus b. And kindly just observe where w represents the weight or coefficient of the feature and b is the bias term. This model works well for regression problem, but in classification, we need our output to be constrained between 0 and 1, representing the probability of belonging to a particular class. We need to apply the sigmoid function. Yes, since a linear model can output any real number, of course, negative infinity to positive infinity. We need a transformation that maps these values into a valid probability range of 0 and 1. So this is achieved using sigmoid function that is defined as sigma of z. Yes, here it is. So sigma of z is equal to 1 divided by 1 plus e to the power, that is e raised to the power of negative z. Dear friends, by applying this function to our linear model, we obtain p of y equal 1 given x equal to 1 divided by 1 plus e raised to the power of negative w transpose x plus b. This transformation ensures that output is always a valid probability, making it suitable for classification. If the probability is close to 1, yeah, the model is confident that the instance belongs to class 1. If it is close to 0, yes, the model predicts class 0. Okay, so let we just discuss about the step 3 on log odds function. Dear friends, rather than modeling the probability directly, logistic regression operates on log odds scale, that is logit. And the odds of an event occurring is defined as, that is odds function, which is equal to p of y equal 1 given x divided by 1 minus p of y, which is equal to 1 given x. And taking the natural logs on both the sides, we obtain the logit function. And kindly just observe, dear friends, this logit function we just specified as log of p of y equal 1 given x divided by 1 minus p of y equal 1 given x, which is equal to w transpose x plus b. This equation establishes a direct linear relationship between the input feature and the log odds of belonging to class 1. The sigmoid function is simply the inverse of this transformation. Okay, so let me just discuss about the step 4 which is the one decision boundary of a classification. Let I just specify decision boundary of a classification. Dear friends, once we obtain the probability P of y equals 1 given x, yes, we classify the instance of one of two classes using the decision threshold typically just set as 0.5. So kindly just observe y hat equals 1 if P of y equals 1 given x is greater than or equal to 0.5. Otherwise, the y hat, it will equals to 0. So this threshold can be adjusted based on the application. For an example, in medical diagnosis, a lower threshold might be used to catch more positive cases, even at the risk of some false positive. Let us just go with the step 5. Here, I just want to discuss about defining the loss function. Dear friends, we are here discussing on a binary classification. So here the loss function, we are going to discuss it binary cross entropy. Dear friends, when we just have to train the logistic model, we need a loss function that evaluates how well our prediction probabilities align with the actual class label. A natural choice in the binary cross entropy loss, also known as this log loss function, which is defined as, yes, L of, kindly just observe, L of theta, which is equal to -1 over n times the summation from I equal 1 to n of y sub I times log of h theta x sub I plus 1 minus y sub I times log of 1 minus h theta of x sub I. Difference here, yi is the exact actual label 0 or 1, and here x theta x sub I is the predicted probability, and of course we are having, that is 1 to n, that is n is the total number of training examples. This loss function has an important property. It penalizes incorrect confident prediction more heavily. For instance, if the actual label is 1 but the model predicts a probability close to 0, the penalty is very high. And here, to minimize the loss function, of course, we just need to optimize our model. Optimize the model by using a gradient descent. Okay, so to minimize the loss function, we use gradient descent, an iterative optimization algorithm that updates the model parameter. That is, the parameter you can just get updated, that is two parameters, W and B, that is to reduce the error. So the gradients, that is partial derivatives of loss function with respect to each parameter, are computed by using the updated weights. And kindly just observe, dear friends, here W sub j, which is updated as W sub j minus alpha times the partial derivative of L of theta with respect to W, that is partial derivative of W sub j. Dear friends, here alpha is the learning rate, and here L of, that is L of theta, is the loss function. And here gradient descent helps find the optimal value of this W and B to improve classification accuracy. So this process continues until convergence, that is ensuring that the model finds the best set of weight that minimize the log loss function. And dear friends, in simple terms, in our model, confidently predict the correct class, so the loss is low. So if you are predicting the correct, the loss would be low. So let me just have this is the prediction and loss. But if it predicts the wrong class with high confidence, the log is high. Our goal is to minimize this loss function so that our model makes more accurate prediction over time. But wait, there's a challenge. If our model memorizes this training data, instead of learning general pattern, it may perform well on known data, but fail on unseen example. This is called overfitting. And of course, we are also able to reduce that overfitting by regularization. So to prevent overfitting, logistic regression can incorporate regularization technique which penalize large coefficient. So we have two types of regularization. L1, that is lasso regularization, which encourages sparsity by adding a penalty proportional to the absolute value of the weight. And here it is just defined as L1 of theta, which is equal to L of theta plus lambda times the summation from j equals 1 to the d of absolute value of theta sub j. And L2 regularization, that is ridge. This shrinks weight towards 0 by adding a penalty proportional to the squared value of the weight. And here the equation is L2 of theta is equal to L of theta plus lambda times the summation from j equals to d of w sub j squared. And here this lambda is a hyperparameter controlling the strength of regularization. And dear friends, logistic regression is a simple yet powerful algorithm for binary classification task. And here it is not yet concluded. Till now we just having the discussion with binary classification. And I'm just going to give you a small information, just making a comparison of binary classification and towards multi-class classification. Dear friends, binary classification refers to a problem where the goal is to classify input into one of two possible categories. This means the target variable has only two distinct values. It can be as a 0 or 1 or true or false or yes or no, like that. And binary classification is commonly used in problems where an event either occurs or does not occur. So the classifier learns from past example and predicts whether new instance belong to class 0 or 1 based on the input feature. And here multi-class classification is a machine learning problem where the goal is to classify inputs into more than two categories. Unlike binary classification where an instance belongs to only one of two classes, multi-class classification assigns each instance to one of three or more distinct classes. Difference, each sample is assigned a single class and the number of possible classes is finite. For an example, in an image classification, let an input image may be classified as like a cat or a dog or a horse, but not multiple classes simultaneously. And how about this binary class and multi-class it works? So kindly just observe, dear friends, binary class models typically predict probability score between 0 and 1. So if the probability is greater than the threshold, of course commonly we just have the threshold as 0.5. So if it is greater than the threshold, the model classifies the instant as like 1. Otherwise the classifications is at 0. So for an example, if I just want to know whether the model that classifies the email as like a spam or not. So probability of spam, which is equal to 0.9, and probability of not a spam is 0.2. Of course, it is classified as like a spam. And here to the same, let me just make it the multi-class classification model. Yes, it output a probability distribution overall possible classes, meaning each class is assigned a probability. So the class with the highest probability, kindly just observe, the highest probability is chosen as the predicted class. For an example, if the probability of a cat, which is equal to 0.1, and probability of a dog is 0.6, and probability of a horse is 0.3, yes, the model predicts dog since it has the highest probability. And this is commonly achieved using a softmax regression. Of course, dear friends, in binary classification, we mainly used on sigmoid function, where in multi-class classification, we use softmax function to convert a raw score into probabilities. And here, what is the function is, of course, P of y equals j given x, which is equal to e raised to the power of z sub j divided by summation of k, which is equal from 1 to k, that is of e raised to the power of z sub k. Difference where this exact k denotes the total number of classes, and here z sub j is the score for class j, and this ensures that all prediction class probabilities sum to 1. Kindly just observe which we have just seen before. So when we just make the summation of everything, it just equals to 1. So allowing of meaningful classification. So here, when we just evaluate the loss function of multi-class classification, yes, here it uses of categorical cross entropy. That is L of theta, which is equal to negative summation from I, which is equal to 1 to n, and summation from j, that is equal 1 to k of y sub I and j times of log h theta x sub I sub j. Dear friends, here the k is the number of classes, yi j is a one hot encoded vector indicating the correct class, and here h theta, I just elaborate light here, h theta of x sub I and sub j. This is the predicted probability of class j functionality. So this loss function penalizes incorrect class prediction and encourages the model to improve classification accuracy. Dear friends, now that we have understand the theory behind logistic regression, let's implement it using the Python and scikit-learn. So in this demonstration, we apply logistic regression to our famous iris dataset and visualize the decision boundary. Okay, so let's get started here. Okay, dear friends, first we need to import the necessary libraries. We'll use NumPy for numerical operation and sklearn for the logistic regression model, for data set handling, and train test splitting, and matplotlib for visualization. Let I just execute this. And with these libraries, we are ready to proceed with loading the data set. Okay. Dear friends, next we load the iris data, a well-known data set in the machine learning, and it consists of a flower spices classified based on features like sepal length, sepal width, and petal length and petal width. For simplicity, we only going to have two features, first two features. Okay, so here kindly just observe, we are just going to have only the first two features, that is sepal length and sepal width, for visualization purpose. So let I execute this. So now that we have X feature, okay, so X feature and label Y. So let's split the data into the training and the testing data. And kindly just observe, dear friends, to evaluate the model effectively, we split the data set into 80% of training data, 20% of testing data. So this allows us to train the model and later assess its performance with unseen data. So with our data set split, we can now train our logistic model. So let us just execute this. Okay. Dear friends, now we create an instance of logistic regression and train it using our training data set. And kindly just notice one thing. Here we have just specified penalty equal to none. That is to ensure that model is trained without regularization. So without regularization, of course, we are not just going to make use of lasso or ridge regularization. Okay, so at this point, our model has learned to classify iris flower based on the given data features. So next, let me just visualize the decision boundary, and kindly just observe, dear friends, to visualize how the logistic model separates different classes, we need to generate a mesh grid. So covering the entire future space. Then we classify each point in the space using our trained model. So here we just creating the mesh grid. Okay, and with X min and X maximum, and the same thing as Y minimum and Y maximum functionality. So this code segment ensures that every point in our feature space is classified according to the trained logistic regression model. Okay, so now let's visualize this result. And kindly just have a note on towards this, dear friends, to make the decision boundary clearly. We will create a color plot where each region represents a predicted class. Additionally, we overlay the actual training data points on the plot. And here we go with the result, and kindly just see, dear friends, the resulting plot display our decision boundary with distinct regions assigned to different classes. So the scattered points represents our training data, allowing us to see how well the model has separated the class. So here we just came to end. Yes, dear friends, let's quickly recap what we did in this implementation. So here the step 1, imported necessary libraries for handling data training models and visualization. And step 2, we loaded the iris data and selected 2 features for visualization. And step 3, split the data set into training 80% and testing 20% as a set, and created and trained a logistic model. And step 5, we have constructed a mesh grid and predicted class label for visualization. And last but not least, the step 6, we have plotted the decision boundary, highlighting how the model classifies different iris species. Dear friends, and that's it. We have successfully implemented logistic regression and visualized how it classifies data using decision boundaries. This example demonstrates why logistic regression is an excellent choice for multi-class classification problem with linearly separable data. Dear friends, in the next session, let me discuss end-to-end project on logistic regression and explore how to evaluate model performance using metric like accuracy, precision, recall, and the confusion matrix. If you enjoyed this tutorial, don't forget to like, share and subscribe for more hands-on machine learning content. See you in the next video, dear friends. Happy learning.